Okay. Good evening to all of you. So in the previous class, we saw that we discussed there are two problems, right? I told you. One is partition of the vertex set and other is the partition of V cross V. So we want to find eigenvalues, eigenvectors of a given graph. For few graphs, very easy to find eigenvalues, eigenvectors, like a complete graph, complete bipartite graph, or few graphs like that. But whereas in general, it is very difficult to find. But there is some techniques can be utilized. One of them is that last class we discussed is equitable partitions, right? So equitable partitions, what we'll do, we'll partition the vertex set in such a way that, so some particular properties, okay? We divide the vertex set, partition the vertex set into cells, so that if you take any two vertices in the set, given cell, they have same number of neighbors in the other cell, right? So but that way we combined all the vertices, one cell into one vertex. Then we'll get a quotient graph or quotient matrix. For them, so a small matrix for the eigenvalues, eigenvectors are easy to figure out. With that, we are able to find the eigenvalues, eigenvectors of the original matrix. That what we discussed in the last class, right? So we have several examples, okay? So today also I will continue with that little bit for some time, maybe half an hour or so. Then later we'll go to the problem number 2. Okay, that is partitioning of V cross V. Okay, so before that, just in the first 5 to 10 minutes, it is about certain graphs which are going to be useful in the next 2 lectures. Okay, not today's lecture, maybe last 2 lectures, that is going to be useful. So you get some time to practice them. That's why I'm giving those. Okay, so I hope all of you know this graph. Just to start with, so that you can communicate with me. Is it anyone can recognize what is this graph is? Can you take guess if you know? Anyone know this graph? Can you take guess? Okay, so this is actually a complete graph. Maybe you are checking everything. So it is a complete graph, right? Yeah. So do you know this graph? Yes. So this is a. Can you share few properties of this graph? Anyone? Just to communicate between you and me. Can you share few of its properties? Anyone? I told it is a complete graph. Okay, you know that there is an edge between any two vertices, right? Yeah, that means any two vertices are adjacent. Okay. What is the other thing? So what are the entries of the adjacency matrix? Can anyone now comment? What is the adjacency matrix of the complete graph? How it look like? Anyone? Okay. So I'm not clear. Am I audible or not? Because you can answer this question easily, right?
Oh, they are typing in the chat box. I think you can unmute yourself and answer.
Yeah, unmute and answer. Yeah, no problem. And also you can tick yes if you want to answer, right? Yeah. So do not chat. Unmute and speak. One of you can unmute and speak. Okay. So you know, right? It is we are calling J minus I. What is J? Can you recall somebody? Can you unmute and speak? What is J? Matrix J. J matrix. Okay. We may forget. So J matrix is all ones matrix, right? Okay. Okay. So this is the complete graph, right? With the 2 vertices, 3 vertices, and all. So there is an edge between any 2 vertices, and so it has n into n minus 1 by 2 edges and all, right? The degree of each vertex is n minus 1. So this we will. It is a very good example for many things. Okay. And actually every simple graph with n vertices obtained from Kn by deleting some edges. Okay. In fact, you want to find all graphs of with n vertices, then that is a subgraph of Kn by deleting some edges, right? That's why it is some people call universal graph. Okay. And you all know cycle graph. Okay. So the degree of each vertex is 2, and these are very symmetrical. We need these. Okay. Yeah. Okay. So another graph we'll frequently use is Cayley graph. What is a Cayley graph? So Cayley graph is that, so from a given a group, I can construct a graph by using that. There are various ways to construct graphs from a given group. But this is one technique that let G be a group and S be a non-empty subset of G, does not contain identity element. Then Cayley digraph or graph is associated with a pair G comma S such that, okay, so vertices are elements of the group. There is an edge between them if X into Y inverse belong to S. Okay, yeah, that is a definition. So there is an edge between them. So there is a set, S separate set is there, right? That is subset of the group. So whenever X into Y inverse belong to S, then we will say that. Okay, yeah. So that is the definition of a Cayley graph or digraph. Okay, when this set S is inverse closed, that means whenever S is there, S inverse also there. If it is inverse closed, then we'll get an undirected graph. Okay, so you are familiar with, and not only that, its cardinality equal to it is a regular graph. It is a regular graph, K regular graph, where K is equal to the cardinality of S1, right? Okay, we'll see one example. So I hope you already come across this because other lectures are going on. Yeah, so I'm sorry if it is repetition. Okay, so look at this S3. Okay, the elements are, 1, 1, 2, 1, 3, 2, 3, like that, right? Okay, I took my set as S is equal to 1, 2, 1, 3, and 2, 3, right? Okay. Now, is it inverse closed? What is inverse of 1, 2? Itself, right? They are transposition, so they are self-inverse, right? They are elements of order 2. They have their own inverse actually, right? And look at the graph you construct, then we'll get this graph. Okay, this is actually K33, complete bipartite graph. Do you have any questions in this? Do you want to ask any? You have any questions? Raise your hand. Raise your hand means in the reactions there is a raise hand button. You can click and you can ask, or you can ask directly, unmute and speak, because number of participants are less, no issue. Okay, so I am assuming that you are clear with this. Okay, one of the best example is that Pele graphs, right? Very nice graphs. Okay, what are Pele graphs? Pele graphs are that, so they are actually Cayley graphs from the cyclic group. In particular, I take some p power n, where p is a prime number, right? So prime power, so z p power n. So q, I am taking q is equal to p power n. Okay. So here vertices are elements of the group Zn or finite field fq, right? Yeah. In particular, I am taking fq, right? Fq is a finite field with q elements. Sorry, now I'm told Zn, not Zn. Finite field. Okay, I'm sorry for that. Yeah. Okay, so I'm taking elements from the finite field fq. Okay, and there is an edge between them. Their difference is a square. That means a quadratic residue. Okay, so you know that when q is congruent to 1 mod 4, then difference we are taking q is congruent to 1 mod 4, and we are taking fq, that is finite field with q elements. Okay, so the vertices are elements of that finite field fq, and there is an edge between them. Their difference is a square. Okay. Okay, so the why I'm taking q is 1 mod 4, then in that case, if q is some x is a quadratic residue, minus x is also quadratic residue, so that I'll get the set is going to be inverse closed set. So I'll get a Cayley graph. We'll get undirected graph. Okay, if q is congruent to 1 mod 4, then we'll get a directed graph. Okay, this is a nice graph, diameter 2, so many nice properties will be there. So I will take up later. Okay, today I'm just introducing this. If you find time, please go through them. Okay, so any questions? Okay, so another graph, easy to understand for you, Neisser graphs. So there are lots of papers on this chromatic number key, and its eigenvalues, eigenvectors actually found by using the equitable partitions. Very interesting topic. So Neisser graph, in particular, Godsland Royal book, there is a chapter for this exclusively for Neisser graphs. Very, very big. So looking like one graph, but it has lots of properties. Okay. What is a Neisser graph? So here you take a set with n elements. Okay. The vertex set is, so k element subsets with k elements. Okay. I take a set with n elements. Now I'll collect all k element subsets. That means subsets with k elements. Okay, so we look at the vertex set is A is a subset of 1 to n such that cardinality of A equal to k. Okay, and so you understand the vertices. Vertices are subsets of 1 to n with the k elements. Okay, each vertex is a subset with the k elements, and there is an edge between them. Their intersection is empty. Okay, so this graph is meaningful when n is greater than or equal to 2k. At least come se come n value should be greater than or equal to 2k. So number of vertices, easy to see how many k subsets will be there with n elements and choose k, right? So number of vertices are n choose k. And the degree of each vertex also easy to figure out because there is an edge between them. Their intersection is empty. So, so if I take one vertex with k elements, then other vertex should not have any of these elements common. So I need to look at n minus k elements in the remaining set. Then I need to choose k elements from that. How many those possibilities are? That many. That is the degree. Hope this part is clear, right? Okay, these have very nice properties. I will discuss that in a while. So automorphism group is very easily to determine. It is a vertex transitive graph. I will also bring that in a while. Okay, and one of the main thing is that this Lausage proved one nice theorem, chromatic number. So one of the standard open problems. So he solved later. So there are very nice properties and nice things about Neisser graphs. Okay, yeah. So we are interested in that. In particular, my k is equal to 2. That means I will collect all the 2 element subsets with 2 elements. Okay, then that graph is very nice. It is n choose 2 regular, and later, so it has nice properties that if I take 2 vertices, if they are neighbors, then they have exactly n minus 4 by n minus 4 choose 2 neighbors. Okay, if they are not adjacent, that means their intersection is non-empty. Then they have exactly n minus 3 choose 2 vertices adjacent to that. Okay, these type of graphs are called strongly regular graph. I will define clearly, but my intention today is that please go through what are Neisser graphs, try to understand. In particular, these k and 2. Okay, so I'll give an example for that to understand what I'm saying in the last slide. Okay, look at this. Okay, so somebody know what is this graph? Can you comment, please? We discussed in the last class. I myself discussed. Can somebody recognize what is this graph? Can you unmute and speak?
Peterson graph, sir.
Peterson graph. Okay. So what are the elements in here? How we constructed this here? So can you see the vertices? What you can say about vertices? Vertices are what? They are subsets of a some set. What is that set? They are subsets of 1, 2, 3, 4, 5, right? And 2 element subset with 2 elements. Okay, 1, 2 is a subset of 1, 2, 3, 4, 5 with 2 elements. Like that I collected, right? And so those are the vertices. So how many vertices will be there? 5 choose 2. There are 5 subsets of size 2 from 1, 2, 3, 4, 5, right? So those are the vertices. There is an edge between them. Their intersection is empty. 1, 2, and 3, 5, there is an edge. Okay. So the way we colored is that these are the coloring. Okay. Chromatic number of this graph is 3. Okay, that is fine. Now get back to the thing, right? So are there any triangles in this graph? Are there any triangles in this graph? So there is no triangle. Can you see why? Okay. What do means it has a triangle, right? That means I need 3 sets. They are mutually adjacent, right? Why that is not possible? Think about. Okay. Yeah. So it is not possible. Okay. That is no 2 adjacent vertices have a common neighbor. That means you take any 2 vertices. They how many neighbor they have? 0 neighbor. So that is independent of the vertices you choose, right? You take 2 non-adjacent vertices. They have exactly 1 common neighbor. Okay. Yeah. So you need to check all these things. Okay, that's why I'm giving you beforehand. Okay, so this is the property of the strongly regular graph. Strongly regular graph means that if you take any two vertices, number of common neighbors is usually independent of the vertices chosen, but it depends upon whether they are adjacent or not adjacent. If they are adjacent, so all vertices which are adjacent have the same number of common numbers. It is independent of the vertices you choose. Similarly, all vertices which are non-neighbors all have the same number of common neighbors. Those graphs are called strongly regular graphs. Okay. Okay. So yeah, so we'll discuss this, and the graph diameter of this graph is 2. Okay. Another graph I will introduce, that is Johnson graph. Okay. What is a Johnson graph? So here also we'll take k element subset of n element set. Okay. So that is number of vertices are again and choose k. And there is an edge between two vertices. If their intersection has k minus 1 elements. Okay. Then easy to see the degree of each vertex, and they have very, very nice structure. Okay. Later we'll see that there are distance regular graphs and all. Okay. So my intention today to introduce these problems is that if you find time today or tomorrow, okay, then you please go through and have some graphs. Okay. I also gave some examples here. You can see this. Okay. So what I done here, I again take a set with 4 elements, right? Set with 4 elements, 1, 2, 3, 4. And I collected all 2 element subsets, right? 1, 2, 1, 3, 1, 3, 1, 4, like that. There is an edge between them. So they are sets with 2 elements, right? So when there is an edge between them, their intersection has 1 element common. Now, in the Neisser graph, intersection is empty, but here k minus 1 elements, right? Yeah. And here you can see. So we got these 2 graphs. Somebody can tell me with 3 subsets with 3 elements and subset with 1 element, what is happening? What is the graph you got? Somebody can comment. Johnson graph. Okay, with 4 elements. So
in these 3 elements, 2 are common. 2 numbers are common.
Yeah. Okay. So then what is the graph you
different?
got? Which graph you got? Funny. Good. That is good. So can you recognize this graph? How many vertices are there? And so
It's complete looking like.
it's a complete graph, right?
Yeah.
Yeah. What about even if I take singletons also? Singletons means the intersection should be one less element, right? That is 0.
It's also
That means
complete.
it is also complete, right?
A
So
cycle.
yeah, no, it is also complete graph. You can see.
Yeah.
Okay, so Johnson graph, you take n minus 1 subsets or singletons, then we'll get a complete graph. Okay, they are part of it. Okay. Okay, so these are some of the things I just gave one example to make it more clear. 5 elements and 2 element subsets I took. Okay, number of vertices, number of edges, degree, and all, so that you can check. And also, it is also strongly regular graph, meaning you take any 2 vertices. I will explain, I will give definition later, okay, thoroughly, and we'll discuss very from beginning. But in the meantime, if you want, you can check. What is a strongly regular? It is a regular graph. And the second point is that you take any 2 vertices. If they are adjacent, any 2 adjacent vertices have same number of common neighbors. If they are not adjacent, they have the same number of common neighbors. Okay. Yeah. Okay. In this case, number of vertices are 10. 6 is the degree of the each vertex. And adjacent vertices, any 2 adjacent vertices have exactly 3 common neighbors. Any 2 non-adjacent vertices will have 5 common neighbors. It is the actually line graph of K5 also. It is a complement of Peterson graph. Like that, it has very nice properties. Okay. Okay, so now I am going to the last some previous class topic continuation, right? Equitable partitions, right? Yeah. Before that, so I just want to test or know what you know about permutation matrices. Okay. So you know something about S3 permutation group, right? You all know, I hope. What is the meaning of 2, 3 here? Somebody can tell me. What do you mean by 2, 3?
Transposition.
That means 2 mapped to 3 and 3 mapped to 2 and 1 mapped to 1 only, right? That is the meaning, right?
Yeah, one to one, and then 2 to 3.
Okay. So what is it actually? S3 is, in general, what is S3? Set of all bijective maps, right? 1,
Yeah,
2, 3,
from
1, 2, 3, set of all bijective maps. Okay.
yes.
Yeah. So we'll write them in a compact way like this. Okay. Okay, good. Okay. So can you see that I can also express these permutations as a permutation matrices? Okay. What is that? For example, one meaning is 1 goes to 1, 2 goes to 2, 3 goes to 3. That I can express as identity matrix. Okay. What is that 1 comma 2 meaning? 1 goes to 2 and 2 goes to 1 and 3 goes to 3. Okay. So these are all matrices. Okay. So here in S3 usually they are functions. So it is a group with respect to composition of functions. But we can convert that into matrices. Then it is a matrix multiplication. It is a group with respect to multiplication. Right. So these are matrices are called permutation matrices. Okay. Do you know something about these matrices? Any properties you know? Anyone want to comment? Any property you know? Anything you want to comment on these matrices?
It must be satisfying all the properties of groups at least.
That is okay. You take all these 6 elements, 6 matrices. So it is already a group with respect to matrix multiplication. It is same as that original group. Okay. It's just a representation.
Yes,
Okay.
sir.
It's just so Rajinikanth in one movie is Baba, in another movie is Basha, right? But same guy. Okay, in a disguised form, but the same thing. Okay. So these are same groups, okay, in different forms. So they are isomorphic. Actually, they are same. Okay. But I'm talking about each matrix. Do you know something about these matrices? One thing is
This
that, yeah, says please.
this matrix contains only zeros and ones, the
That is
permutation
number one.
matrix.
Wonder good. Number one. Okay. Any other second property? Any other property?
Row sum and column
And
sum
then
is
column
1.
sum.
So row sums and column sums are same. Then what is that? What are those matrices?
Double matrix, double stochastic.
Double stochastic. That is actually, I'm now happy. I'm looking for that answer that I got. Okay. Yeah, these are all double stochastic matrices. Good. Okay. Yeah. Okay. So that is number one. Other thing is that they are orthogonal, right? You look at there are orthogonal matrices. Okay. So every group actually we can represent. This is called regular representation. So groups are actually abstract objects. So we can represent them concrete. That is called group representation, right? So yeah, okay. So this is one representation of the thing. And rook placement. Okay. For example, I have 4 rooks. 4 rooks are there. I need to put in a chessboard, a 4x4 chessboard. In how many, how can I put so that they will not kill each other, right? You see that I put, so rook in column 4, right? Yeah, so 5 roots here. Yeah. Okay. So this is exactly what it is actually 1 map to 4, 2 map to 1, 3 map to 3, 4 map to 5, and 5 map to 2, right? It is a 1 1 on 2 map. Okay. So we need to put rooks in such a way that they will not come in the same row, same column. Then they will not kill each other. It is also a rook placement. Okay. So these are all same actually. Number of bijective maps from with set with n elements itself. So number of ways of placing n rooks on n cross n chessboard, number of permutation matrix of ordering, all of them are same. Okay. Okay. So these are all same. So any questions? Is it okay?
Professor,
Yes, sir.
Please.
can you explain that 1, 2, 3 permutation and the corresponding matrix in this 3?
Okay. So yeah, so there are different people look at different ways. Okay. Some people look at column wise, I'm looking row wise. Okay. So for example, you take this particular matrix. Okay. Are you able to see my cursor, please?
Yes.
Yeah. Okay. So this is corresponding to 1, 2, 3. So 1 map to 2, right? Here 1 map to 2, 2 map to 3, 3 map to 1. Okay. That is, I'm in the first row, 1 map to 2, second row, 2 map to 3, third row, 3 map to 1. Okay.
So it's not the characteristic vector like the column vector.
No,
Okay.
no, that is different. Yeah. So
Okay.
that previous class, whatever we discussed, that is different from this.
Okay.
Yeah. Okay. Thank you for asking. Yeah. So yeah, that the doubt may be there. Yeah. Correct. It is not related to characteristic matrix. Okay. Okay. So okay. Now I'm going to automorphism group of a graph. Okay. Yeah. So this is a starting today, right? So what is automorphism group of a graph X? What is an isomorphism between two graphs? X and Y are two graphs. I need to find what is an are they isomorphic or not? Okay, is anyone want to comment? When you say that two graphs are isomorphic, you know that's why. In any class, even in regular class, if voice changes, it will be better. Correct? That's why I'm asking. It is not like that. You all know. But it is better that one of you speak, then other people concentrate. Otherwise, it is become monotone, right? Yeah. Somebody can comment, please. The question is that when you say that two graphs X and Y are isomorphic, what is the definition? Two
They
graphs
have the same structure.
okay. What is the meaning that they have same structure? Okay, it's a
Number of
map.
vertices and edges should be same,
Okay.
and other
Okay.
When we can find a map from vertices to other vertices and which preserves edges.
Very good.
adjacency also.
Adjacency, that is actually what he told is correct. See, some of you are telling that they have same number of words, the same number of edges. They're all fine. Okay. Once they are isomorphic, all these are equal. But that is not the definition. Okay. For example, when I have two people are there, they are twins. Okay. So they are same. We say then you need to show that nose is same, eyes are same, ears are same, everything. But to show that they are not equal, you need to show that at least one place there something is missing. Okay. You see his right eye and his right eye, they are different, right? But to show isomorphic, you need to show everything is same. That is very difficult. Okay, you cannot show that whatever you show, something will be there. So you know that many times we'll get some WhatsApp or something. Can you see difference between these two map? So can you see some difference in these two pictures, right? That is very difficult, right? Yeah. Okay. So what is the definition? There is a bijective map from vertex set of X to vertex set of Y such that they preserve the adjacency. What do you mean by preserve the adjacency? In the groups, in the graphs, main thing is the adjacency, right? So they have to preserve the adjacency. That is what first person told. Preserve the structure. Whatever the subject you take, groups, isomorphic means, so they preserve the binary operation there. Okay. In vector spaces, they preserve that operations, right? Like that, whatever you take, there is some structure that has to be preserved. That is correct. Here, adjacency need to be preserved. What do you mean by adjacency preserved? So bijective maps, all bijective maps are not isomorphisms. Only those bijective maps in which edges go to edges. Means, so v1 comma v2 is an edge in X, then f of v1, f of v2 should be edge in Y. Then we say that these two graphs are isomorphic. Now automorphism means X to X itself. And one onto map preserves the adjacency. Okay, so how to check? So one of the major problem is that in the group graphs, given two graphs, they're isomorphic or not. That is a very tough problem. Okay, so many people try to solve that problem. Still, it is not clear whether it is in P or NP. Number one. Number two, many people tried actually, looking very easy and all. I can try. So that's why some people call it is a isomorphism disease problem, graph isomorphism disease problem. So they thought that it is easy and enter into it, and entire life they tried. Okay, so but not able to succeed. Few people, right? So that's why they are called graph isomorphism disease. Okay. Okay. So is there a way? Okay, how to find? Okay. So now we'll convert this problem into our matrix theory problem. Under this, so what we are doing? So we are taking automorphism group. Okay. Automorphism is a permutation of the vertices. So it is one onto map. So they have the permutation of the element vertices, right? So it is a automorphism group is a subgroup of Sn. Okay. But you know, just now we observed each that one by onto bijective map, you can convert it into a permutation matrix, right? Okay, for example, so we already explained you 1, 2, 3, I can write like this, right? Okay, so we can convert each automorphism as this, okay? And now we need to check which what are automorphisms, right? So now we will going to discuss about that. How to check given element is an automorphism or not. Why I'm converting into matrix, that I will going to tell you in a while. Okay. So, but better that you please look into these aspects also. Okay. So some questions I asked here, better check those things also. Okay. For example, so I have a matrix. Okay. All entries are one J, right? We are calling J. So somebody can point out that what is this product? 1, 1, 1, 1, 1, 1, like that. I'm multiplying to A, B, C, D, F, G, H, I. Okay. What is the product I'll get? Can somebody
Like
comment?
column sum.
So this into this will get column
Second
sum.
column.
What is the first row? Can you tell, please? Thank you very much. Can you tell me the first row?
Like first column sum, second column sum, third.
Yeah.
column
Okay.
sum.
Good. Good. Yeah. It is a column sum. What about this matrix, please?
This is row sum of the first
Row
one.
sum. Yeah. So the question is that when they are equal. So J into some PG, right? Okay. No, forget about PG, right? So for example, this into this equal means row sum should be equal to the column sum, right? Okay. So some matrix is commuting with all ones mean. Some matrix is commuting with all ones means that is row sum should be equal to the column sum. Do you know some matrices where row sum equal to column sum? Do you know some matrices where row sum
Just
equal
now we
to
have seen like permutation also, row sum and
permutation
column.
also, right? They're all doubly stochastic matrices. So
Yeah.
every doubly stochastic J, right? So some matrix is commuting with J means row sums equal to the column sums, right? Yeah. Permutation matrices, every permutation matrix with commute with J. Now, so with that, can I find automorphism group of Kn? Right? What is a, yeah, so that is the question, right? The question is that now, so what is automorphism group of Kn? We need to figure out. But before that, I am asking one question by using this. So permutation matrices are commuting with J, that you now understood, because permutation matrices are doubly stochastic. Column sums equal to row sum, so they are commuting with J. Hope you are clear with that. Now you know adjacency matrix of complete graph. That is J minus I, right? Only diagonal are 0, remaining all 1. That means that J matrix minus identity. Okay. Is it every permutation matrix commute with J minus I? My question clear? Is it every permutation matrix commute with J minus I?
It depends on what elements we have here, because that will take only the two elements of the column or row.
Okay. Okay. So
Because
I'll ask one more question. Okay. Is it a permutation matrix commute with identity matrix?
yeah, it will commute.
Since every matrix commute with identity, right?
Yeah.
So there is no issue. Now
Yes.
permutation matrix commute with J. Yes, because
Yeah,
row
yeah,
sum
it's
equal to column.
commuting.
Now every permutation matrix will commute with J minus I. Yes. Right. Okay. So every permutation matrix commute with my adjacency matrix of the complete graph. Okay. So I'll come to this why I'm asking these questions now. Okay. Yeah. Okay. So now I'll tell you why I'm asking commuting part. Okay. So there is a beautiful thing. So how to find the automorphism group of a graph. Okay. So that is this. So G is an automorphism of the group graph X if and only if that the permutation corresponding to that permutation matrix corresponding to that permutation that commutes with A at adjacency matrix. Okay. That is the beauty. How to check a given graph? Sorry. given permutation of the vertices is an automorphism or not. Okay, if and only if G is a automorphism, if and only if its permutation matrix commute with A. So the proof is very simple. We'll see that. Okay. Any questions? We'll prove it now. Okay, and we'll see a lot of applications of this problem. Right. Okay. So how to prove this, right? Okay. Let A be the adjacency matrix of X. So I take G as an automorphism. So, okay. So permutation of the vertices V1, V2, Vn. Okay. Right now I'm not telling it is an automorphism or not, just a permutation of the vertices. Okay. That is, let us take G of Vi, G maps Vi to Vh and Vj to Vk. Some. Okay. G is a permutation. So it maps some vertex Vi to Vh and Vj to Vk. Okay. So far so good. Okay. Now we take the PG. Okay, you know PG is a permutation matrix. Each row, each column contains exactly one entry, right? So now I'm checking what is PG into A. So what is ikth entry of PG? PG into A, ikth entry. You know that. So it is T equal to 1 to N PGIT plus ATK. Right? Okay. Yeah. So that is so here. This is a permutation matrix. Only one entry is 1. All others are 0 in that particular ith column. Okay. Yeah. So when my so when it is Vi mapped to Vh, okay, then my T is equal to H, then this is 1. In all other places it is 0, right? So this is PGIH only. Remaining all are 0. Okay. So I have AHK here. Okay. So I'll get AHK. So I'm not telling that G is automorphism or not. Just I'm taking some permutation and I'm checking what is PG into A. Okay. Now similarly, I'll compute APG into IK. Right. So here, so now my K is fixed. I'm changing T. So rows in a row also, permutation matrix in a row also, only one entry is 1, others are 0. Okay. So now here, so Vj. Okay. So at J, so this is 1, right? In all other places it is 0. Aij. Okay. So this is just PJA IK entry, APJ IK entry. So AHK, AIJ, right? These two I got. Now these are now commuting means what? PG into A equal to APG, then AHK equal to AIJ. And you know that since matrix entries are either 0 or 1. So that means both are 1 or both are 0. That means both are edges, both are not edges, right? So whenever VH, there is an edge between VH and VK, and there is an edge between I and K. So G is an automorphism. Am I clear about the proof? Yeah. Okay. So to check now, to find an automorphism of a group, automorphism of a graph X, what is that I have to figure out? I take its adjacency matrix. I'll find out all the permutation matrices commute with A. I'll collect them. That forms a group. That is called automorphism group of X. It's a different way to tell what is automorphism group of X. Collect all permutation matrices of size n by n. N is the number of vertices. Then which are commuting with A. Okay. So that forms a group. Why it forms a group? Identity anyhow there. If two matrices are commuting, then their product also commutes with A. Easy to check. Okay. And they are already invertible matrices. So all of them will be satisfied. Okay. So now the problem boils down to find automorphism group of a graph. It is easy. It is now to find all permutation matrices of n by n. Again, we'll feel that is easy. No. The reason is as n increases, number of permutation matrices are unfactorial. That is tough to check. Okay. Yeah. But one thing is that two graphs are isomorphic or not can be converted to automorphism group problem. So if you're able to solve automorphism group in polynomial time, then you can solve isomorphism problem also in polynomial time. Okay. But automorphism problem solving meaning that you need to find out all permutation matrices commute with A. But that is not easy. So, but what is the advantage of stating in matrix theory? Okay, it is easy to show now that automorphism group of X equal to automorphism group of its complement. How do you prove this? Right? Somebody can comment. Do you have any idea? What is that I want to show? Automorphism group of X equal to automorphism group of its complement. What is that I have to figure out? What is that I want to prove? Okay. So that means that all permutation matrices commute with A. They're also commute with the adjacency matrix of X complement. Can somebody tell me what is the adjacency matrix of X complement? Complement graph. Suppose A is the adjacency matrix of X. What is the adjacency matrix of X complement? Are you studied that? You come across that?
Adjacency matrix of complete graph minus adjacency matrix of X.
Very good. Because its complement means you are complementing from the complete graph, right? But what is the adjacency matrix of the complete graph?
J minus I.
Okay. Now what is that you are subtracting? What is the now adjacency matrix of X complement?
J minus I minus adjacency matrix of X.
That is J minus I minus A, right? Now clear? Yeah, good. Now, if some permutation matrix commuting with A, is it commute with J minus I minus A also? Yes, because every permutation matrix commute with J. Every permutation matrix commute with identity. And it is already commuting with A. Then it is commute with J minus I minus A also, right? So that's very easy to show. Okay, now I am showing the proof, right? Okay. So B commute with J if and only if row sum equal to column sum. Just I am again wrote one more time. Right? Okay, consequently every permutation matrix commute with J. So if permutation matrix PG commute with A, then PG commute with J minus I minus A also, right? That is exactly the adjacency matrix of A complement. This matrix theory version is easy to understand. Okay, automorphism group of X equal to automorphism group of X complement. Okay, hope we'll appreciate this. Any questions? Do you have any questions? No questions. Okay. Good. Okay, so we'll move forward. What is the beauty of these automorphism groups? So if G is an automorphism, then it takes so G maps V to some G of V, right? V mapped to G of V, its image, right? Then their degrees need to be equal. Okay, and U and V are two vertices. So if there is some distance between them, then after their images, G of U, G of V, they are two vertices. Their distance also same. So automorphism group preserves the degrees. Automorphism group preserves the distances. Like that, it preserves many things actually, because these two are isomorphic, right? It preserves many things. Okay. So now, so the thing which we are going to see is that automorphism groups acts on the vertex set. It's called a group action. Which takes one vertex to other vertex, right? So it is a map from G cross X to X. Okay, so automorphism group acts on the vertex set. That is, it is a map from G cross X, G cross V of X. Sorry for G cross V to V. Okay, G cross V to V. It takes vertex. So you take a group element, it acts on the vertex, take to other vertex. That's called group action. So group action will give partition the vertex set. Those are called orbits of the partition. So I hope my feeling is that group actions in India in particular not studied properly, but that is needed for me here because orbits will give the equitable partition. That is the reason why I'm introducing automorphism group is that we are looking for equitable partitions. Why we are looking for equitable partitions? We need to partition the vertex set such that I'll get a smaller matrix whose eigenvalues, eigenvectors from that I can get the eigenvalues, eigenvectors of the original matrix. But how to find that these equitable partitions? One method is this. You take any subgroup of an automorphism group, any subgroup. Entire group also you can take. Okay, now look at its action on the vertex set. So what is the action here? What is the equivalence relation? X is related to Y. There is an element, there is an automorphism which take X to Y. That is an equivalence relation. Those equivalence classes are called orbits. Okay, so that is a partition of the vertex set.
Excuse me, sir. When we take the like set as means over which we are this group will act, the group of automorphism, then whatever that vertex set that will be same as the over which we have taken the automorphism group X.
Yeah. See, what is happening? We took a graph, right? X. We took some
Yeah.
graph. Then it has some vertices. Okay.
Yes.
And afterwards, we found the automorphism group of that. Automorphism group means all 1 onto maps which preserve the adjacency. We collected all of them. That forms a group. Now I'm saying that you take what is this group? What is this group will do? It acts on the vertices. Acting on the vertices means if I take a small g belongs to automorphism, it takes vertex v to some other vertex, right? Okay, so like that it is acting. Acting means it takes one vertex to another. Okay, so that is called a group action. So
Generating
here,
edges.
no,
Through the X.
it is taking vertex set to again vertex set.
Yes, sir.
Okay, yeah. So what is happening is that that automorphism group takes vertex set to vertex set means that it permutes the vertices. It permutes the vertices. Okay, then so those which are so I take one vertex where it goes. Okay, I take another group element where it goes. I'll collect all of them. They are called equivalence class. Okay, that is called orbit of that particular vertex. Okay, I take one vertex. I'll take different group elements where these group elements are taking V2. Okay, that is called an orbit. Okay, so you collect all orbits. They partition the vertex set. Okay.
Then within the orbit, graphically, what relation those vertices will have?
They have same degrees. All those vertices have same degree. They have very nice, beautiful properties.
And then this action we can also define in several ways. So it is only.
You are correct. Action can be defined several ways, but this action I am taking that whatever I started with. So I collected all these as a automorphisms, right? Yeah. So
Okay.
they naturally V goes to something else, right? So when they are going, degrees will be preserved. The distances are there. So many things will be preserved. So you are correct. So those classes, that is the reason actually why you are taking automorphism. All of them have the same property. Okay. Any problem, we will do equivalence relations mainly because of that, right? So they are all now collapsed to one. Okay, that is the idea.
Thank you, sir.
Thank you very much. Yeah, correct. Okay, so that now our objective is that those who are there in the last class, so you know that equitable partition, right? These orbits actually give the equitable partition. That is this theorem about. So O1, O2, OR are the orbits of the partition. Okay. Then if I take two elements in this cell OI, then you can easily see that okay, their degrees are so there is an automorphism which takes phi of u to phi of. So that maps phi maps OJ to O. Yeah. So OI to OJ. I think there is some mistake here. So yeah. Okay. Okay. So now there is a one thing. So what is happening is that you take any graph X, you take its automorphism group, and you take its subgroups. those orbits will give an equitable partition. That is what I want to convey. So some orbit partition, some equitable partitions are coming from the automorphism and their subgroups. Okay, so for example, now I'm defining one thing, ds of A, it is set of all double stochastic matrices that commute with A. A is a matrix. I'm collecting all double stochastic matrices that commute with A. For example, if my A is J, what is the then ds of J? My A is J matrix, all ones matrix. Okay. I told you ds of A is set of all double stochastic matrices with commute with A, right? Now my A is J. Then can you tell me what is ds of J? This is certainly all double stochastic matrices. It means every double stochastic matrix commute with J, right? If my A is the adjacency matrix of complete graph, then also that is, right? Yeah, okay. That is actually, there is a nice result that, okay, I'll get back to that. Okay, yeah. So I hope you understand the set DSA. So DSA is set of all double stochastic matrices with commute with A. Okay. So what is the property of double stochastic? What is a double stochastic matrix? Entries are non-negative. Number one, each entry is non-negative, and row sums equal to 1 and column sums are 1. Okay. Sum of all the entries is going to be n. Okay. Not required, that automatically comes from. So A is adjacency matrix of a graph X. Then if every extreme point of ds of A is a permutation matrix, then we'll say the graph is a compact graph. So there is a person called Tinofer who defined this. A graph is said to be compact if, okay, every extreme point of ds of A is a permutation matrix. Then that graph is compact. Actually, this permutation matrix, it is in the automorphism group of. So I'll explain this now thoroughly. Note that ds of A is it is a convex set, right? ds of A is set of all double stochastic matrices. It is a convex set. One can check. You take the convex combination of double stochastic matrix, again a double stochastic, that you can check easily. Okay. So it is also contain permutation matrices, right? So now we are checking. So we are taking all automorphisms of X. Okay, we take all automorphisms that. Okay, so if X is compact, then automorphisms of X are precisely the extreme points of ds of A. Extreme points means you know that it is a convex set. Then they are written as a convex combination of the some matrices, right? So if they are permutation matrices which are coming from the automorphism of A, then it is called a compact graph. Okay, there is a nice result. Birkhoff-von Neumann theorem. Every double stochastic matrix actually a convex combination of the permutation matrices. That is exactly that matrices. That is exactly related to complete graph. Every permutation matrix is an automorphism, right? So Birkhoff-von Neumann theorem is same that. So complete graphs are compact. Okay, sorry if this is a little complicated thing. Okay, yeah, okay. So just I want to, why I'm telling this thing is this for this theorem only. Okay. So if X is a compact graph, what is a compact? Again, I will repeat once. All double stochastic matrix which compete with adjacency matrix are in the convex combination of the permutation matrices, which are in the automorphism of X. Okay. If the graph is like that, then every equitable partition is also an orbit partition. That means in the compact graphs, equitable partitions, orbit partitions are same. Okay. Yeah. So just to tell this, I brought all that, but don't worry about you can ignore this particular concept, okay? But I want to bring that there are graphs in which orbit partitions and equitable partitions are same, okay? So there is a beautiful paper by Godsil. I will show in a while. Okay? You can go through it. If you have doubts or you want to discuss more, please we can discuss next class, or you can write a mail to me. We'll discuss it. Okay. Yeah. Okay. So so a graph is said to be vertex times 2. Automorphism group acts transitively on that vertex set. That means there is only one orbit. Okay. Yeah. So for example, Kn is vertex times 2, complete graph, cycle graph or vertex times 2, like that. Okay. In fact, we can show that Cayley graphs are also vertex times 2, right? So Cayley graph is vertex times 2. How to show? So xy is an edge. Okay. Then so you take G is an G belongs to G is in the automorphism group of, right? Automorphism group of X. G is an automorphism, right? Then you can easily say that this is an edge if and only this is an edge, right? So and so we can easily check that AB inverse takes A to B. The group element AB inverse maps A to B. A and B are two elements in the group. This group element takes A to B, right? Yeah. So because of that, it is a vertex transitive graph. Okay. So why I'm telling this particular result? Yeah, please.
Sir, you said something compact graph.
Yeah.
What
Please.
what was it?
Compact graph means that so you collect all the doubly stochastic matrices which commute with X. Means adjacency matrix of X. Okay, I'll go slowly. X is a graph, right? Okay. Then we have its adjacency matrix. Let us say A is the adjacency matrix of X. Then I'll collect all doubly stochastic matrices which commute with A. Okay, that I'm calling as DS of A. So that is all. Okay. Now, okay, that is one thing. Now you have automorphism group of X that we can express in terms of the permutation matrices, right? Okay. Then X is said to be compact if every doubly stochastic matrix which commute with A is actually a convex combination of these permutation matrices. Those are in the automorphism of X.
Oh, okay, sir.
See, what is happening is that I can write that doubly stochastic matrix. Convex combination means what? Lambda 1 times plus lambda 2 times something, but they're all permutation matrices. So, you know, basis may, vector spaces may, what is that basis will do? Every vector can be expressed as linear combination of the basis vectors, right? Like that, every doubly stochastic matrix is expressed as a convex combination of the permutation matrices. Okay, that is actually in general true, but compact may you are confined to only automorphisms of X, only those permutations which are in the automorphism of X. Yeah. So if I'm collecting double stochastic matrices which commute with A, that is a set. In that, every matrix is actually convex combination of the automorphisms of X. Then we'll say that X is compact. So if the graph is compact, then equitable partition orbit partitions are same. Okay. Yeah. So I'll can I move forward?
Yeah,
What
sir.
about the converse of that one? If both are same,
Okay. That is converse, right? Yeah. Good question. So if it is an orbit partition, automatically equitable partition. That we proved. An orbit partition is an equitable partition, but equitable partition need not be orbit partition, right? But in compact graphs, it is true. Okay, so Tinofer, one person started working on this particular problem, and he also classified trees are compact, complete graph is compact, like that. Okay, sorry, I'm not going into depth. Okay, so I'm sorry for introducing this. I just telling this is not a good way to take up a topic. So, but otherwise, I had to go a lot of details here. Okay, But why I'm introducing it? Because this is one thing that orbit partitions will give equitable partitions. Okay, are there any extra? Sometimes extra, but in a compact graph, no. These are the only. Number one. Number two, there are many open problems. Still, all compact graphs are not figured out. Somebody want to work in that, one can work. Okay, I will show the one paper of Garcil in a while. You can check that and you can work on that. Okay, and Tinofer himself proved that all trees are compact, cycles are compact, but still it is open. So there is a beautiful things. If you know compact, there are other advantages also there. Yeah. Okay. So can I? Okay. Is it okay?
I think she asked whether does it characterize compactness? If every equitable partition is an orbit partition, does it implies that the graph itself is compact?
Okay. Okay. That is what you are looking.
Maybe I'm asking.
Okay.
Hmm.
Yeah. So that is true. Yeah. That is true, because we saw in the previous class that every equitable corresponds to some double stochastic matrix. We can check in the slides I showed someplace. Okay. Yeah, that can be used to check it. Okay, so can I proceed, please? Okay, so look at this. One last point I want to add related to equitable partition. If my graph is vertex standstill, okay. So you know that equitable partition, we have an equitable partition. The equitable, that quotient matrix, okay, quotient matrix eigenvalues of quotient matrix are eigenvalues of x. But sometimes what happens? Some eigenvalues of x may miss. We are saying that all eigenvalues of the quotient matrix are eigenvalues of x, but we may not get all eigenvalues of x, right? Okay, that we checked. We have lots of example last time, but my graph. So there is a partial answer to this problem. Okay, when all eigenvalues of x are eigenvalues of the quotient matrix, one particular theorem is there. If my graph is vertex times 2 and pi is an orbit partition, and it have one cell with only singleton, then that equitable partition automatically become an in that case the all eigenvalues of B are eigenvalues of E. Okay. Yeah. I'm sorry, I'm not giving proof for this. Okay, so just I want to touch some points here. So now I will go to the next concept. Okay. Yeah, I know that in the last lecture we took only one topic and we went depth. So just to conclude, I told some big concepts without proper examples and all. Okay, but I'll go to the second problem now. We will work it out properly. Okay, yeah. So now onwards. So I'm going to the problem number 2. What is the problem number 2? So partitioning the V cross V such that our goal is to find out all graphs which are polynomials in a given graph, right? So for that we need to partition V cross V, and I'm going to that. Okay. So for that I'll ask few questions. I hope you will respond to these. So A is a finite, non-empty finite set. What we can say about the relation on A? Somebody can comment, please. Some of you are teaching also this concept. What do you mean by relation on A? A is a subset. Okay. So
It's just
take
like edges. If it is graph, then edges.
no. So no graph theory and all. So simple. Okay. Take a deep breath and get ready.
Is subset of like cross.
Subset
Relation
of.
is a subset of A cross A.
That's it. That's what I'm looking. Exactly. Thank you. Yeah. So relation means simply a subset of A cross A. That's it. Okay. Yeah. Yes. Okay. So right. So R is a relation on A, then MR corresponding the 0 1 matrix. Okay. So I will construct a matrix with rows indexed by A, columns are indexed by A. Okay. It is subset of A cross A, right? If that ordered pair is there, I'll put 1, otherwise 0, right? So finite set I told. So this is MR is a mod A cross mod A, cardinality of A. Okay, I'm telling cardinality of A cross cardinality of A set, right? A matrix. Okay, size of the matrix is n cross n, where n is the cardinality of A. Okay, that is also a 0-1 matrix, right? So there is a 1-to-1 correspondence between relation on A and a 0-1 matrix, right? That is the beauty. Okay, there is a 1-to-1 correspondence. You give a relation, I'll give a matrix. If you give a matrix, I'll give a relation, right? Okay. So for example, a set with n elements, how many symmetric relations are there? Okay, before that, how do you check a relation R is symmetric or not? By using the matrix. R is a relation on A. That means R is a subset of A cross A. And I'm telling it is symmetric relation. You know symmetric relation means, right? Can I recognize given relation symmetric or not by using the corresponding matrix?
If the corresponding matrix is symmetric, then it
Yes.
shows.
Yeah, correct. If my matrix MR is symmetric, then it is symmetric. Because if AB is there, BA has to be there, right? AB is 1 in the MR, then BA has to be 1, right? Yeah. So how many symmetric relations are there on a set with n elements? That is equal to the number of symmetric matrices with n elements, 0-1 symmetric matrices, right? Okay. That is actually the number of graphs, including the self loops, right? If you exclude the self loops, that is a number of graphs. Okay, so there is a connection, right? Symmetric relation is nothing but a graph only, right? Okay, so somebody may not see this way, then you can check. If you put diagonals are also 0, then okay, then the symmetric relation with the diagonals are 0 without self loops. Okay, yeah, so that is exactly 2 power n into n minus 1 by 2, right? Otherwise 2 power n into n plus 1 by 2 number of symmetric relations. Okay, yeah, so let us see this. A is equal to 1 comma 2. What is A cross A? You know, right? So you know what is R1. What is the matrix related to R1, right? R2, R3, R4. What is union of Ri? You can easily check. Can somebody tell me what is the matrix corresponding to R1? MR1. It is a 2 by 2 matrix. What are the entries? I think it is very trivial, it seems. I am asking very simple questions, maybe. I'm sorry for that.
First diagonal entry is 1, the remaining cell 0.
Yeah, so first entry 1, remaining 0, 0, 0, right? Next 0, 1, 0, 0. So 0, 0, 1, 0 and 0, 0, 0, 1. So can you think of what is happening? What are R1, R2, R3, R4 matrices are doing? Can you think of something? What are these matrices? MR1, MR2, MR3, MR4. What are those? They are exactly the basis, right? For MR2 of M2 of RK, right? Okay. What I want to say that our diagrams actually we can think of basis for the M2 of R also. Okay, they are directed graphs, right? 1 comma 1 is a self loop. 1 2 is a directed edge. 1 to 2, 2 to 1. Okay, and 2 to again a self loop. Okay, so okay, what is the vector space spanned by them? So you understand that vector space spanned by them is entire set of all 2 by 2 matrices. Okay, what is the vector space spanned by this? MR1, MR4, MR2, MR2 plus MR3. I added them. Okay. No need to tell now. So anyhow, I will share this thing. You can check it. Is anyone want to comment?
What vector scalar multiplication, and that is usual scalar multiplication.
Yeah, usual scalar multiplication. Yes.
Mm.
Matrix addition, usual matrix addition, usual scalar multiplication, right? So I'm asking what is these are the matrices, 3 matrices. What is MR1 1 0 0 0? What is MR2 plus MR3 0 1 1 0? One matrix. MR4 is 0 0 0 1. Okay, what is the vector space spanned by them? Okay, so you can check that these are exactly the symmetric matrices. Okay, set of all symmetric matrices. So last question here. So I added MR1 plus MR4. Okay, R1, R4 I added. MR2, MR3 I added, right? So can you somebody say what is the vector space we get here? And also you check that is it closed with respect to matrix multiplication also. In the vector space we will not ask, right? Is it closed with respect to multiplication? But here I am asking. Okay, so check that part also. Okay, yeah. So one more question related to this. If A equal to 1 2 3, I took R0 as 1 1 2 2 3 3 and R1 is remaining all. Okay, so somebody can tell me what is MR1 matrix that you tell, right? Identity matrix 1 0 0 0 1 0 0 0 1. Can you tell me what is MR0 plus MR1? Okay, what is MR1? Somebody can comment on that. I removed the diagonal 1 1 2 2 3 3. R1
J
is
minus I.
J minus I. So what is J minus I? That is exactly the adjacency matrix of cycle graph, sorry, complete graph, right? In this case, it is cycle also. 1 2 3 pay. Okay. So I am asking whether it is closed with respect to multiplication also. I'm just asking some questions. Okay. If you find time, please check them. Okay. I'll explain with one example now. So I took this, right? Okay. So this is a graph. Okay. This is a cycle graph, you know, right? Okay. Now, what is this graph related to this? What is the distance between 1 and 3 in this graph? Cycle graph C4. Distance between 1 and 3.
2.
2, right? So I am collecting the what is here I am putting edges between them. The distance is 2. Okay. Vertices are as it is 1 2 3 4 only. There is an edge between them. The distance is 2. Okay. So 1 and 3 distance is 2. I'll put an edge. 2 and 4 distance is 2. I'll put an edge. Okay. Yeah. Good. So far so good. Okay. What are these corresponding things now? Okay. This is actually I'm not put self loops, but there is self loop. Okay. This is 1 1 2 2 3 3 4 4. Okay. So this is 1 2 1 4. Actually 1 2 means there is an edge from 1 to 2. Also there is an edge from 2 to 1. It's undirected, na? Undirected graph. Okay. So actually, so what is the cardinality of R1? I told that AB meaning AB BA, right? I'm looking subset of V cross V. My V is equal to 1 2 3 4. V cross V contains 16 elements, right? Okay. So can somebody tell me what is this? These 3 sets are doing R0, R1, R2.
Partitioning.
Partitioning which set?
Like V cross V.
Yeah, V cross V. V cross V ka partition hai simply, right? And what are the elements I took? One is identity. Okay, unko chhod do. R1 meaning the edges actually, right? 1 2 2 1, 2 3 3 2, all that. Total there are 8 are there. Okay. And these are the others are edges of the what is this graph? Can somebody comment? Okay, distance 2 I told, that's fine. Somebody can tell other way. For example, if I add these two graphs, if I take R1
Complete graph, it will be
graph, right? So it's complete graph, so it is actually complement, right?
complement.
It is also think as a complement also. Okay, good. Okay, so far so clear? Yeah. Okay. Now look at the adjacency matrix. What happens if I add all these three? If I add all these three, what I'm going to get? J matrix,
J.
right? And also what if I add A1 and A2? I'll get a complete graph. Adjacency matrix of the complete, right? So these are why I'm doing all this. Okay, you have a question. Okay, let us see. So these are already you answered before that. Thank you very much for that. A1 plus A2 is the adjacency matrix of the complete graph, right? Okay. So one more beauty is that Hadamard product. Hadamard product means component-wise multiplication. Okay. So actually that is also called bad student product. Okay. See what happens when you add two matrices, we'll add component-wise, subtract also component-wise. Suddenly when you multiply, so a row le lo, column le lo is a bull. But if you ask the student, naturally what he will do? He will do component-wise only, right? So that's why some people call bad student product. Don't worry about that. So it is called Hadamard product or sure product also. Okay, what is this meaning? We'll multiply component wise. Okay, can somebody tell me what is the Hadamard product of A1 and A2?
Zero matrix.
Zero matrix, right? So any two of them you take because they are disjoint, they are partitioning. Okay, so it is actually closed with okay. So that is the beauty, right? So they are components. That's one thing. Okay. Okay, I'll come to that slowly one by one. Okay, what is A1 square? You already done this problem, right? A1 is the adjacency matrix. A1 is this, right? A1 is this adjacency matrix of this graph. You know what happens if I square the adjacency matrix, right? What happens?
Is it 2n?
No. When you have adjacency matrix, if you square it, what are the entries in the matrix? A square may elements. ijth entry is what? It is a number of walks of length 2 from I to j, correct?
Yes, sir. Yes, sir.
You remember that? Okay. So what are the diagonal elements in A square? You done that. Diagonal elements are exactly the degrees of the vertices, right? What is the degree of each vertex here? 2, right? So that's why I'll get 2 times A power 0. A power 0 means identity matrix. So A1 square equal to 2 times identity plus A2. You can check that. So we'll get there is a walk of length 2 from. There are two walks of length 2 from 1 to 3. How? 1 to 2, 2 to 3, 1 to 4, 4 to 3, right? Here in this graph. Okay, that is exactly A2 ka, right? Okay, so you will get A1 square. You can just square it and check. I'll get 2 times identity plus 2 times A2. Okay, I hope it is very easy to see. Okay, then what is happening in this now, right? So now what is A2 now? A2 is equal to 1 by 2 times A1 square minus 2i, right? That means my A2 is also polynomial in A1. Are you understanding that? A2 is a graph. A2 is adjacency matrix of the other graph, complement. But now that is a polynomial in A1. Okay. Are you okay? Then what are the eigenvectors of A2?
Same as A1.
Because A2 is a polynomial in A1. So if you have some matrix, okay, if you have some matrix, you take its polynomial, both the matrices, right? If you have the same eigenvectors, eigenvalues are also P of lambda 1 like that, right? You take a matrix A, P of X is a polynomial. P of A is also a matrix. It is a polynomial in A. Eigenvectors are same, luckily, but eigenvectors are substituting the eigenvalues, P of lambda 1 like that. Okay, so both will have the same eigenvectors. Okay, that is my idea. Second problem too. Some graphs are actually polynomials in my original graph. Then eigenvectors, if I found for my first graph, I can find eigenvectors of other graph also. Okay, eigenvalues are also easy. Okay, that is here very simple example. You can follow easily. That's why I gave this. Okay, yeah. So somebody can.
Then they also span the same eigenspace.
That's what. When their eigenvectors are same, the same eigenspace, right? Yeah, I'll give more examples. Okay. One more point I want to ask you here is that what are the eigenvalues of A? A1, adjacency matrix. It is a cycle graph, right? Yeah. So can you see that what are the eigenvalues of this matrix? Yeah. Yeah. So can you comment? And you can see that it is a complete bipartite graph, right? Can you tell me which complete bipartite graph? Hello, am I audible? Which complete bipartite graph? C4.
K22.
K22, right? You remember we started with the complete bipartite eigenvalues, right? What are the eigenvalues of Kmn? You remember?
Plus or minus root mn.
Plus or minus root mn, and 0 is an eigenvalue for that many. So what are the eigenvalues of here? K22, root mn, m and n are same. So root of -4 and root of 4. So plus or minus 2. And other eigenvalues are 0, 0, right? So eigenvalues of this graph are 0, 0, plus 2, minus 2. It is a bipartite graph complete. So there is symmetry about the eigenvalues also. All of them are done. Okay, good. Now what are the eigenvalues of, okay, without evaluating this, what are the eigenvalues of this graph? You can see what is this graph? Can somebody tell me? Is it a connected graph? No, right? It is not connected. It is a disconnected graph. But what is that components, each component?
K2.
K2. What are the eigenvalues of K2? You know. So K2 eigenvalues are 1 and -1 only, right? Yeah, because adjacency matrix is 0, 1, 1, 0, right? Otherwise, you know already, n-1, comma, -1, like that, you already done. Okay, so it is repeated. Spectrum of the disconnected graph is spectrum of the individual, right? So -1 2 times, 1 2 times. Okay, now you compute this also, you'll get the same answer. Okay, just I'm telling you that how to see all the things. Okay. Okay, so hope you are clear. Okay, now actually that is my topic now. Now onwards, next two lectures, today remaining part and next lectures is related to this. Okay, what are all graphs which are polynomial in the given graph? Okay, how to recognize them? So these are the books I followed. Okay, Godsil book. Okay, I'm telling previous class and this class or in future what are the things I. So Godsil book by Algebraic Graph Theory by Godsil and Royal, NLBix Godsil and Royal, Bapat's book Graphs and Matrices. So there is a one book Distance Regular Graphs by Brower, Cohen and Numier, and Philip Davis Circle and Matrices. And there are distance regular graphs can be constructed some combinatorial design theory. Okay, so this is a nice book on that combinatorial designs. Okay, by Douglas Stinson. Okay, and there is a Raghav Rao, he also written on this. And these are the papers I. So there are many. These are the some of the main things I referred. Okay, compact graph and equitable partitions. This is what I'm talking about. I quoted all those results from this paper. Okay, yeah. So this is a very big paper, around 131 pages paper. So this is this exactly connected to which graphs are polynomial and other graphs. Okay. Yeah. So anyhow, I will no need to follow this. I'm just telling that where I'm collected. Okay. There is survey paper. This survey every year they will update. Okay. There is survey on distance regular graphs. It is keep on continuing. And there is a Fauzal Atik and Pratima Panigrahi. They wrote a beautiful paper on the distance spectrum of distance regular graphs. They used equitable partitions to entire paper is on equitable. By using equitable partition, they found the spectrum. So very nice paper. You can understand now easily. Okay. So that is the idea. So now I'm going to the actual thing. Okay. So for that, I need something I need to define called adjacency algebra. Okay. Sorry, today I think, of course, graph theory is a discrete mathematics. Today my topics also discrete, not on single topic. I'm very so first topic is on equitable partition. Second part is I'm going to the second problem. Okay. Okay. So here I want to tell you an algebra. Okay, F is a field. When we say that a ring is an algebra, in the algebra course, there is a definition for algebra itself. Okay, so a ring is said to be an algebra. It is also vector space. It has both the structures, vector space structure as well as ring structure, and it is compatible with that matrix multiplication and the field multiplication. Okay, so vector space over a field, right? So it satisfies. So in the ring there is a matrix multiplication. So it will compatible with that multiplication. Then it is called a algebra. Okay, vector space plus ring plus compatibility. Okay, but you know some algebras actually. C is an algebra over R. Okay, every field is an algebra over itself. Mn of F is an algebra. You know that Mn of F is a vector space. Also, it has a ring structure, right? So yeah, so set of all linear transformation from V to V. Fx itself, set of polynomial algebra. Okay, so Fx is called it is an algebra. It has both. It is a ring as well as vector space. Okay, and if you take any group G, Fg is an algebra, right? Okay, that's fine. Now algebra you understand. Now we want to define adjacency algebra. If okay, so I'll just skip this part. Okay, and so these also. But why I given this to motivate you to take to the adjacency algebra. So I just to tell this particular thing. Okay, you know what is Q of alpha? You come across this in the field theory somewhere.
Is it extension field?
Yes, correct. So what is Q of alpha? Adjoining alpha, right? You know something, you may come across Q of root 2, right? Okay.
Yes.
Yeah, something. Okay, so I want to connect it to the adjacency algebra. Okay, so what happening is that you take an element alpha. Okay, alpha belongs to complex number. When we say that it's an algebraic element, alpha is a root of a non-zero polynomial, right, in QX. Then we'll say that algebraic element. Okay, so if in alpha is an algebraic element, then I can define a map phi alpha that is called evaluation map Q of X to C. How we define? So Q of alpha of f of X equal to f of alpha. Okay, I'm taking polynomial and I'm evaluating at alpha. That is called evaluation map. You can easily check that it is in a homomorphism, onto homomorphism. Okay, and so it's a range. You know, by fundamental theorem of homomorphism of groups, rings in particular. Okay, you have this. Okay, so it is so this Q of alpha, it is a range. Okay, onto homomorphism. So it is isomorphic to this. What is M alpha of X? It is a minimal polynomial of alpha. For example, Q root 2 is isomorphic to Q of root 2 is isomorphic to Q of X
quotient x square plus 2.
X square minus 2, right? Yeah. So C complex number themselves isomorphic to R of X quotienting X square plus 1. You know these things, right? Yeah. So if you understand the same thing, okay. Now you take a matrix A, you collect C of A, set of all polynomials in A. Okay. So C of A becomes an algebra. You can check that it is a vector space structure, it has a ring structure. Very beautiful, right? You take one matrix, you collect all polynomials in A. What do you mean by polynomials in A? You take a polynomial and substitute A. Okay, like Q of alpha, right? You want to understand? Okay, again do this. Okay, you take a matrix A, then you compute QA C of X to Mn of C. But now it is Mn of C, right? I'm substituting matrix in a polynomial. I'll get a matrix. Okay, it is a map from C of X to Qn of X, C, right? So again the same. It is onto homomorphism, everything. Okay. Now this is C of A, set of all polynomials in A, isomorphic to this. Okay, C of X quotienting the minimal polynomial of A. But what is the difference between the previous concept and here? In alpha, M of alpha is a minimal polynomial that is actually irreducible also. That's why it is a field. One of you already told it's an extension field. They are already fields. Minimal polynomials are irreducible. But minimal polynomial of a matrix need not be irreducible. Okay, don't worry about that. It is a ring structure. So this actually isomorphic to this also if you want. whenever we need sometime you want to work in polynomial algebra, you can work, but we will need this C of A. Okay, that is actually called adjacency algebra. Okay, yeah, okay. So
M of AX is the kernel here at this place.
sorry, can you repeat, please?
Is this minimal polynomial is kernel of this map?
Yes, kernel of this. Correct.
Because
Yeah, that is so actually what happens now, here also you do the same thing now. How this M alpha of X comes, right? So Q of X is a PID, right? Principal ideal domain. So what is the kernel of that, right? Yeah, you are exactly correct. Okay, so that Q of X quotienting that kernel is isomorphic, right? R by kernel of this is isomorphic to the image, right? That is what fundamental theorem of homomorphism of groups or rings or whatever you take, right? Yeah. So say exactly, you are correct. That is exactly that. That is a kernel. That is a minimal polynomial of A only. But luckily, if your matrix A is diagonalizable matrix, then you know that minimal polynomial has distinct roots, right? Hence, if A is diagonalizable, so the dimension of C of A is as a vector space is the number of distinct eigenvalues of A. Okay,
yes.
Are you following? When I'm
Yes.
quotienting this MA of X, the dimension of this is easy to see. Dimension of this is that the degree of the minimal polynomial. Okay, these are isomorphic. That means the dimension of C of A as a vector space is the degree of the minimal polynomial of A. If it is diagonalizable, then exactly the distinct eigenvalues of A. Beautiful. Okay, my C of A dimension is the number of distinct eigenvalues of A, right? Okay, overall this is the thing. Dimension of C of A, okay, is the dimension of the minimal polynomial that is also equal to the number of distinct eigenvalues of A. Okay, so this is when A is my adjacency matrix of a graph, then we know that A is actually a symmetric matrix. If it is symmetric, it is diagonalizable. Okay, in that case, that C of A, I denote it as A of X. Now onwards, the C of A, I denote it as AX. What is AX means? Set of all polynomials in A. That is a beautiful object. What is that now? It has vector space structure, it has a ring structure, and it is an algebra, right? It is very, very rich structure it has. Okay, so now I take one graph and it is in matrix, then I'll get a beautiful algebra. Okay, so whose dimension also we know, that is the number of distinct eigenvalues or degree of the minimal polynomial. Okay, I'll explain with one example. Okay, look at this. Okay, K3. Okay, so I'll stop in a while. Okay, so you have the adjacency matrix 0, 1, 1 like that. Okay, adjacency matrix, you know, J minus I. Its characteristic polynomial is x plus 1 whole square into x minus 2. We noticed earlier n minus 1 multiplicity 1, minus 1 is an eigenvalue 2 times, n minus 1 times. Minimal polynomial is x plus 1 into x minus 2, right? Its adjacency algebra is this, adjacency algebra. Okay. Only I and A, they generate. Okay, why that is happening? You take A, you compute A square, A cube, A power 4, all of them, right? You can easily check all diagonals are same, remaining are same. That means it is a linear combination of every matrix, every power of A is a linear combination of these two only, identity and adjacency matrix. Another beauty is that these two matrices, Hadamard product is 0. Are you understanding that? The basis of the complete graph, the basis of adjacency matrix of complete graph is simply I and A only. Its dimension is 2. Complete graph has only 2 distinct eigenvalues. Okay, what is its basis? Nice basis it has, I and J minus I. Their Hadamard product is 0. They are disjoint. What is the advantage of that? Then, so which graph polynomial is easy to figure out. I will tell you that. Okay, so one more example, KNN you take. Okay, so KNN. How many distinct eigenvalues are there? Assume that n is greater than or equal to 2. How many distinct eigenvalues are there for KNN? You know that. What are the eigenvalues of KNN? Complete bipartite graph.
plus minus and 0.
How many distinct? 3. So dimension of the adjacency algebra of Kn is 3. So one basis is IA square because I'm taking polynomials, right? But there is a issue here. In A square, we'll get the diagonal element I also will come. Okay. But there is another basis for it. What is that? Identity A and A complement. A complement is adjacency matrix is a complete complement of Kn. What is the beauty about this basis? They are Hadamard product of any two of them are 0, right? They sum equal to J. That means that they have a nice basis. Okay. What is the advantage of this? Now, if I take any graph which is polynomial in A or not, I can easily check. So, in fact, A times A plus B times A complement I take, right? A and B are 0 or 1. Okay. Like that, I'll get all the graphs. Okay. Yeah. So, I'm asked here some questions. What is the dimension of Cn? Okay. So, what is the dimension of Ca when complete graph? I already explained you, but I given for only K3 here, I'm asking in general, Kn ke liye. You can easily check that. So I'm asking that is so adjacency algebra of Kn is same as adjacency algebra of, sorry. So C of Jn also, easy to check. How many eigenvalues are there for Jn? You know that. All ones matrix, n and 0. Kn also the same. Okay. In fact, you can easily check that these are same. Okay. Dimensions are same. In fact, they are equal actually. Okay. One more thing you may need is that set of all. So BA, this is different. What is BA? Set of all matrices commute with A. So there is a difference between adjacency algebra and B of A. In adjacency algebra, set of all polynomials in A, they automatically commute with A. If I take a polynomial, I substitute A, that automatically commute with A. Polynomial in A commute with A square commute with A, A cube commute with A plus A square commute with A, right? They automatically. But if I collect only those matrices commute with A, that is a bigger. Okay, that is also a subalgebra. That is also an algebra. You take one matrix, collect all matrices commute with A. There is a vector space, ring structure, everything is there. Okay, and in fact, this is subalgebra of the CA is a subalgebra of BA, right? So, what is the dimension of B of IN? This I will ask. You can easily tell. What are all matrices commute with identity matrix? What are all matrices which commute with identity matrix?
All the matrices.
All the matrices. So it is actually Mn of R. Okay. Yeah. So what is a matrix which commute with Jn? Okay. So you ask these questions also. Then you will see that this is a beautiful result. Okay. The dimension of B of A, all matrices commute with A, is actually related to the multiplicities of the eigenvalues of A. Okay. M1 square plus M2 square plus Mr square. Lambda 1, lambda 2, lambda are the distinct eigenvalues of A. Okay. Yeah. So proof, if you want, I can explain. That proof I saw in Circular Matrices by Davis. Okay. The beauty of this result is that if all eigenvalues are distinct, n distinct eigenvalues, then multiplicities become 1, 1, 1. Right. In that case, so number of distinct eigenvalues equal to the dimension of, right? In this case, these two going to be coincide. Which one? C of A and B of A will coincide. Otherwise, actually, C of A is a subalgebra. But if all eigenvalues are distinct, then they will coincide. Okay. These I will use later. Okay. There are graphs in which all eigenvalues are distinct. Okay. If you want, you can check path graph. Path. Okay. All eigenvalues are distinct. In that case, what is the beauty about that? Every matrix is commute with adjacency matrix, actually polynomial in that. You see the beauty. Somebody is a polynomial that automatically commutes, but commute does not mean it is a polynomial. Okay, but if all eigenvalues are distinct, these two will coincide. Okay, so that is one example I want to tell you. Okay, so can I tell only this and stop? Do you allow me?
Yes, you can take care.
Yeah, okay, only one. With that I will stop. So that look at this particular matrix, right? Do you recall this matrix earlier we come across? Somebody tell me. This corresponds to which permutation, right? 1 map to 2, 2 map to 3, and 3 map to 1, right? Yeah. You square it, what happens? If you square it, okay, you can easily check that they will move like this. If you cube it, I'll get identity. That is exactly right. 1, 2, 3, you square it, 1, 3, 2 will come, right? If you again square, if order of that element as a group is 3, right? We'll get identity. Okay. So now you know that so dimension of CA is less than or equal to n. Why? Dimension of the set of all polynomials is less than or equal to n, because dimension of CA is the degree of the minimal polynomial, right? So degree of the minimal polynomial, why less than or equal to n? Minimal polynomial is divide the characteristic polynomial. Characteristic polynomial degree is n. It cannot be minimal polynomial degree cannot be greater than the characteristic polynomial, right? So minimal polynomial degree is at most n, right? So dimension of the you take any matrix C of a dimension, that is if A is adjacency matrix, that is adjacency algebra. Otherwise also we can discuss set of all polynomials in A whose dimension is at most n. But here these are all you can see that W3, W3 square and W3 cube, are they independent or not? They are independent. Why they are independent? Head mod product is 0, right? Component wise they are 0. They are okay. So one cannot express as linear combination of other. They are linearly independent. So the dimension is at least 3, but at most 3. So it is equal to 3. Okay. Can somebody tell me what are the eigenvalues of this matrix? See, this is the polynomial satisfied by omega. Right? Somebody tell me what is the polynomial corresponding to this? I substituted W3 in which polynomial?
Cube root.
No. So I'm asking, you are correct. You are saying something else. You are a little ahead. I'm asking, I substituted
Cube.
x cube is equal to
Minus 1.
1. X cube equal to 1. Actually, that is the minimal polynomial of that. What are the roots of x cube equal to 1? Nth roots of unity, cube roots of unity.
1 omega omega square.
Correct. They're all distinct, right? So this matrix have 3 distinct eigenvalues. That means that every polynomial which commute with it, every matrix which commute with it actually polynomial in that. Okay. So don't worry. Now just another beauty is that you take in general Wn. Okay, I'm explaining with the W3. You can extend it to Wn. So it is also form a group. Actually, it is a cyclic group. One of the beauty about this matrix is that these powers themselves form a cyclic group. Their eigenvalues also form a cyclic group. That nth roots of unity. Beauty, right? At least for me, it is very beautiful. Okay, you take a polynomial, all its roots forms a group, cyclic group. Okay, and okay, this matrix also forms a group. Okay, so here they are equal. Okay, so permutation matrix has eigenvalues, eigenvectors. Okay, is it a doubly stochastic? Yes. Okay, so there is a graph for which it is adjacency matrix. Somebody can comment on that. Graph or a directed graph? This is it adjacency matrix of some directed graph or a graph? Yes, right. It is a 1 to 2. There is an edge. 2 to 3, 3 to 1. Directed, but 1 to 2, 2 to 3, 3 to 1. Right? Yeah. Okay. Yeah. So what is mean by B is in CFWN? It is a polynomial, right? So can you know the properties of B? Okay. So in particular, just I will ask this. What is Wn plus Wn power n minus 1? Is it a 0-1 matrix? Is it symmetric? These are the problems. Can somebody predict Wn? You understood. First row is 0, 1, 0, 0, 0. Second row is 1, 0, 0, 0, 0. Right? Sorry, 0, 0, 1 like that, right? 0, 0, 1, 0, 0, 0. Third row is 0, 0, 0, 1, 0, 0, 0, like that, right? Last row is 1, 0, 0. Right? What is Wn power n minus 1? You add them. What you are going to get? Is it symmetric? Okay, at least tell me how many ones in there in each row. Can you say that? With that, you can predict. In Wn, how many ones are in each row? Only one, right? In powers also, they are all again permutation matrices. Okay. Each row contains exactly 2 ones. Actually, it is cyclic. This is adjacency matrix of cycle group, cycle graph. Okay. Wn plus Wn power n minus 1 is the adjacency matrix of cycle graph. Okay. Then can I get eigenvalues now? What are the eigenvalues of Wn? Nth roots of unity. Correct? Then what are the eigenvalues of cycle graph? So cycle graph, what is the, it is a polynomial in Wn. What is the polynomial? X plus x power n minus 1, right? Now you substitute the eigenvalues, you will get the eigenvalues of cycle graph also, right? In fact, you can say, you can look that many graphs are actually polynomial in Wn only. Okay, so with that I will stop here. Okay, you can easily check that these are actually called circulant graphs. A graph is a circulant graph. First row is rotated. That is exactly the polynomial in Wn. You see that how it is happening, right? You can check one graph. Okay, so let me. So are you able to see that what is the A times W3 plus A times identity plus A times W3 plus A times W3 square? Okay, what is A times identity plus B times W3 plus B times W3 square? Okay, what is the first row? We'll get ABC. Second row, CAB. Third row. So first row only will circulate. Okay, it rotate. If you know the first row, I'll know all the rows. Okay, not only that, my matrix actually polynomial, that is the polynomial. First row gives the polynomial. Okay, these graphs are called circulant graphs. A graph whose adjacency matrix is circulant matrix, then they are called circulant graph. Okay, yeah. So my first row is this. Then there is a polynomial, and so my circulant graph actually that adjacency matrix actually polynomial in this, right? Okay, so what happens is that so this is the Fourier matrix. This is the set of all eigenvectors of my Wn, and these are all eigenvectors of all circulant matrices. Means all circulant graphs. For all circulant graphs, these are the eigenvectors. Okay, every circulant graph is a polynomial in Wn. For all circulant graphs, I can get the eigenvalues also, just substituting nth roots of unity. They are sums of nth roots of unity. Okay, so that is the beauty about circulant graphs. Okay, so I will start with this. Okay, so A is a circulant matrix with the representative polynomial gamma of x. It is diagonalizable. These are the eigenvalues, and eigenvectors are exactly those. Okay, cycle graph. Eigenvalues are these. Zeta n is a primitive nth root of unity. Okay. So I gave that earlier. Okay, so can I stop here?
Yeah, we can stop here. I'll stop recording.